big ideas of this course, which is mathematics in 3 dimensions. So up till now, for years and years as you've studied mathematics, it's been about in terms of x and y. X-axis, y-axis, you can draw it on a flat sheet of paper. But we live in 3 dimensions, at least in terms of space. So understanding 3 dimensions and understanding that mathematically is, as you might imagine, incredibly important. And I think incredibly cool. So now let's learn how to do it. Number 1, we need a coordinate system. So the coordinate system that we're going to use, there are many ways of writing a coordinate system. We mentioned polar coordinates. That's one way to think of coordinates. Right now, we're going to talk about the standard thing that you would think. If you have an x-axis and a y-axis for 2 dimensions, then for 3 dimensions, we're going to add a z-axis. Okay. So where is the z-axis? Well, if you have an x and y axis on your paper as you normally would, then the z-axis would actually come straight out and poke you in the eye. Okay. Now we get to the problem of the fact that we often use a pencil or a pen and a sheet of paper in order to do mathematics. So this now becomes very hard to draw. So how are we going to draw a 3-dimensional object on a 2-dimensional sheet of paper? Since you can't literally do it, you have to figure out a way to do a representation. So here are some possible choices. So in the first case, the x-axis is in the usual place. The z-axis becomes our vertical axis. And then the y, then based on that, goes where it has to go. So it's good for some of those reasons, but it's bad because the axes are bunched together, at least in terms of like the positive axes. So graphs tend to get squished together, and it becomes kind of hard to see what's going on. So we tend not to use that particular representation. In the second one, the axes are spread out, but y is on the horizontal axis, and that may be a little disorienting at first. But you're going to have to acclimate to this weird orientation because we're trying to put 3 dimensions of space in a 2-dimensional piece of paper. Okay. So we're going to make drawings. We're typically going to make drawings using this axis setup because they tend to be clear as we're representing things. So there's another option, which is on the right. And so this uses a couple of different conventions. It uses a box, so not axes coming out of the origin, just so the axes don't get in the way of the actual graph, which is going to be some kind of like sort of solid or space-filling shape. And then also notice the z is still vertical, and then x and y are sort of coming off at these angles. Now that particular one was actually made by the professional software Mathematica. I'll use that sometimes to make demonstrations. One of the nice things about Mathematica is that once you graph the object, you're able to rotate the object just by clicking and dragging. You could also do that with Maple, for example. So one comment is that in all these representations, you're going to see z on the vertical axis. Now the reason for this is that many times we're going to think of z as our function. So z is a function of x and y. So our function values are still represented by quote-unquote height. So now let's get a little used to using the x, y, z axes and 3-dimensional graphs. Okay. So graph all the points which satisfy z equals 0. So how do you do that? Well, where is z equals 0? Yeah, exactly. That's actually a really good way to think about it. It's like the ground. So using the, I guess using the second representation, z equals 0 is right here. But then what are all the points that are like that? It's like the ground. So it's sort of like this. Now instead of me making a sloppy, instead of me making a sloppy and imprecise graph, we're going to do it using the software. So there you go. There's z equals 0. So z equals 0, notice that this is like a copy of the standard xy plane. But it's a copy of the xy plane at z equals 0. Where else could you have a copy of the standard xy plane?
Anywhere else.
At z equals 1, z equals 2, z equals 3. Think of z equals 3 as like the ground on the third floor. Spatially. Okay? So next, what about the graph y equals 2? What does the graph of y equals 2 look like?
The plane parallel to the xz plane.
Yes. So it looks like this because, remembering that the y-axis is this slanty one here, there's where y equals 2. So it's going through that point, and then it has to sit where all the points have a y value of 2. So it looks like a plane oriented like that. So 2 comments. First of all, yes, just as z equals 1, z equals 2, z equals 3 were parallel to the standard xy plane, y equals 2 is parallel to what you might think of as the plane created by the xz axes. Now in this particular rendering right here, notice that it's kind of hard to tell exactly where the plane is sitting. It's like a flat plane facing us, but you can't necessarily tell exactly where it's sitting. It could be at 1, 2, 3, da 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 da. So for example, it's nice when you have the software that you can actually rotate it and look at it from several different angles to get a better orientation. Again, this is just one of the difficulties of having to deal with a 3-dimensional picture represented on a 2-dimensional sheet of paper. Okay. And then let's graph x equals 1. So where's the graph x equals 1 going to be? So ones I'm looking like that. So you identify the x-axis. You see the spot on there where x equals 1, and then you see that the plane is going to be slicing through there. And yes, it's going to be parallel to the plane, to the YZ plane, or in other words, the plane with the YZ axes in it. Okay. So now let's start actually doing calculations to describe our 3-dimensional objects. So let's talk about distance in 3 dimensions. So suppose you have 2 points. What's the distance between them? So just as an interjection, in case it wasn't clear, so now when you describe a point, you don't just give x, y values, you give x, y, z values. We're in 3 dimensions, you need 3 values to describe the point. Okay. So what's the distance between 2 points? So the nice thing is that it's really just an extension of the formula in 2 dimensions. And once again, it comes from the Pythagorean formula. So it shouldn't be too hard to remember, but also here is an explanation with a graph to show you what's going on. So in case you want to convince yourself, here's a little derivation. And the derivation comes from drawing another point B. And A and B, without going through the details, notice that they're in the same plane. So we already know how to describe the distance between A and B. And then B and C are just on a straight line. So it's easy to describe that distance. But then A, B, and C form a right triangle. So then we can say what the distance is between A and C because it's the hypotenuse. And then you just have to sort of chase through the notation with x1, x2, y1, y2, z1, z2. So there's a proof of the distance formula for 3 dimensions. Let's use it. So let's find the distance between these 2 points. So distance equals the square root of what? So 4 minus 2 squared plus negative 3 minus 3 squared plus 0 minus negative 1 squared. And you just got to work that out. So 2 squared is 4, negative 6 squared is 36, and then 1 squared is 1. Square root of that whole thing is the square root of 41. So I'll just make one comment here. So you can see that this extends pretty nicely from 2 dimensions to 3 dimensions. Turns out you can extend this beyond 3 dimensions into any number of dimensions. Now, talking about 4, 5, or 6 dimensions is beyond what we're going to do in this class. But at least in terms of doing a calculation, it's actually pretty straightforward to find the distance in, say, 7 dimensions between 2 points. Next, what is a vector?